Um, Aldo Procacci is going to speak on improved bounds on cluster expansions of the abstract polymer model.
Okay. Well, first of all, I want to thank the organizer for inviting me to this workshop and to the program here in the Unis Institute. And today I will speak about this work, this joint work with Roberto Fernandez as we did in Juan in 2006. So we study the abstract polymer model, which is a model proposed by Kotevsky Price in a CMP paper of 1986. The setting, the model is as follows. I will follow closely the notation of the paper of Kotevsky Price. So I have a countable set P, whose elements are called polymers. To each polymer, gamma is associated an activity Z gamma, which can be in C, but in general, if positive, has a physical interpretation. And there is a reflexive and symmetric relation I in P. So if a pair of polymers belong to this relation, we say that these polymers are incompatible, and we write like this, otherwise they are compatible. Let's now take a finite set inside P, and we can write down the grand canonical partition function in this volume, abstract volume, in this way. Is this sum, and here is the this function is 0 if gamma I, gamma j doesn't satisfy don't satisfy this condition. So substantially, in this sum appear only pairs of compatible polymers. So the cluster expansion, we can do the Meyer expansion of this series. You have seen the Meyer expansion of this series yesterday. Alan Shokal showed this Meyer expansion. One can do the Meyer expansion of this series and obtain a series for the logarithm, a formal power series for the logarithm of the partition function of this gas. These coefficients, which are called Ursel coefficients, are given explicitly by this sum. Here the sum is over connected graph with vertex set 1 to n and edge set in this set in. Sometimes I indicate this set like in. And this notation here means that G must be a spanning subgraph connected of the graph G gamma 1 gamma n. G gamma 1 gamma n is the graph. Sorry, here I was confused. G gamma 1 gamma n, which appear here, is the graph, which has vertex set 1 to n and edge set Ej such that gamma E is incompatible with gamma j. Has an edge only Ej only if gamma E is incompatible with gamma j. And here the sum go over all connected spanning subgraph of this graph. Here Eg denote the cardinality of the edge set of the graph G. So, simple argument shows that to check the convergence of this series here, of this series uniformly in the volume, lambda is okay, is sufficient to control the convergence of a formal Pinhead expansion given by this expression, which is very similar to the logarithm of the partition function. Here now rho gamma 1 gamma rho gamma are positive number already. So if I prove the convergence of this series, of this positive term series, the convergence of this series will imply the absolute convergence of the series of the logarithm of the partition function for all complex Z gamma less or equal rho gamma. And this should be the bound, which is a bound uniform in volume, because what is uniform in volume in 1 over lambda divided the logarithm of the partition function. So in the sec we will focus our attention on this series here, P gamma 0 rho. So let's state our new convergence criteria. Our convergence, new convergence criteria involve the grand canonical partition function associated to the polymer set. Here there is a gamma which are in this P such that they are incompatible with gamma 0. So all the polymers gamma incompatible with a fixed polymer gamma 0. So the partition function for this set has is this one, summing over all n of.
Does it include gamma?
Yes, include the gamma. Yes, as the relation is yes, including itself. The relation is reflexive, so every polymer is incompatible with itself. So the theorem states the following: if I have, suppose that you have numbers mu, and let rho such that rho gamma is less or equal mu gamma divided this partition function for all gamma in the polymer set, then the series we saw 1 minute ago converges and satisfy this bound. So this is a criterion for convergence of cluster expansion. So the updated list of the known criteria for cluster expansion for the Austrian polymer gas is as follows. I put the three together since it is easy to compare. This was the criterion given by Kotevsky-Price in the 1986 paper. 10 years later, Dobruchin found a new criterion which slightly improved the criterion of Kotevsky-Price, which is this one. And our criterion is this one. Clearly, since this function is greater than this, which is greater than this, is obvious that this criterion is better than this, that is better than this. This radius is bigger than this, which is bigger than this, which is bigger than this. Okay. So let's do some remark. Actually, the Kotevsky-Price criterion appear in general is used in this form. Also in the original Kotevsky-Price paper was written in this form. So to get this form from this, you have just to put mu gamma equal to rho gamma e to the a gamma, make a change of variables, and you got, and these criteria became this one, which is, let's say, how people, the criterion which people use in the literature. Concerning Dobruchin criteria, there are various equivalent forms. Here there is one. Yesterday you have seen two other forms, one presented by Kotevsky, the other one presented by Sokal. Well, today I also give a fourth way to rewrite the Dobruchin criteria, and this way appeared is how Miracle Solé wrote the Dobruchin criteria in a very nice paper in Physica, I think, so where he proved by induction in a very simple way the Dobruchin criteria. So I will give also this formula because I will use it soon. So let us, to have an idea, compare these three criteria. We start first by an elementary example, the domino model. I chose this example because it is the one considered by Dobruchin in the paper of 1996. So in these examples, the polymer space is the set of nearest neighbor pairs in ZA, namely P are the pair in ZA such that, here something go wrong, but such that x belongs to y, y belongs to y, and the distance between x and y is 1. So are all the nearest neighbors pairs. So we can suppose that each polymer are constant activity gamma. Here the activity, namely the activity, is the same for all polymer, and the incompatibility relation is the overlapping. So this is a simple gas, and it's simple to test the criteria, the three criteria, and we can make in that criteria the choice, the natural choice, mu gamma equal mu, also independent on gamma for all gamma. So Koteski price criterion give this. And you see that here I have the sum over all the polymers which are compatible with the polymer, which are given polymer, and there are 7 of these polymers. Here is the polymer gamma 0, so there is this, and the polymer itself. So, I have this, and maximizing in mu, I have this bound. Oh, the Dobrushin criterion, here instead I have to make the product that give 1 plus mu to the 7, again, there are 7 of this. And so maximizing the function mu over 1 plus mu to the 7, I get this, and so there is some improvement with the Koteski price, and our criterion yields the following. We have our criteria is rho less or equal mu divided our partition function. The partition function contains only 3 pieces. The one proportional, which we contain 1 polymer, and then there are only the terms, you know, in this function here. Let me go down here. In this function here, I have to sum until 2, because when I sum into the term with n equal 3 already contain polymers all pairwise incompatible. So here I have to sum until 2. And for 2 I have 9 ways to sum 2 polymers in such way that they are compatible. Here, 1 is here, and then 3 possibility here, and and then 1 here, and again 3 possibility here, and 1 here, and again 3 possibility here. So our bound is this one. And you see that there is some sensible improvement respect to the other criterion. A second and less trivial example is the gas of finite subset of a countable set. So in this example, the polymers are finite subset of a given infinite countable set. So polymer in particular have at least a simple structure, which is the cardinality. I can say, I can talk about polymer which big cardinality and low cardinality. And, again, the incompatibility relation is defined by the overlapping. This is the most common realization of the abstract polymer gas in statistical mechanics. Practically, okay. Come on, what? No. Here there is no connection at all. Let's say I have an infinite countable set, and I take the subset as polymer gas. The subset, this view has no structure. In general, view is the for example, is the lattice ZD, and these sets are connected. But let's stay more abstract. So I just consider this. So the Koteski price criteria in this case, so let's use the popular version of the Koteski price criterion, which is this in this case. The incompatibility relation is the incompatibility, is the overlapping. So we use the elementary inequality, also used yesterday by Koteski, this one, and the Koteski price condition is become this one. This condition is very.
So they are not connected really?
Pardon?
They are not necessarily.
Not necessarily
If you have 2 points.
Yes.
The size is 2.
Yes.
So I have infinitely many of them, so the sum is infinite.
No, because the activity can decay. If I have 2 points, let's say far away, there is no structure, the activity can be very small and this sum can converge. For example, in the Camarota paper, polymers was like this. Okay, so but this condition is very popular. Everyone uses this condition. In particular, it's so popular that also Dobrushin used this condition in his paper of 1996 to check the domino model, and he obtained a condition worse than the 1 over 7a, obviously, because this criterion is a little bit worse of this criterion, because I'm doing something worse. In any case, this is the condition which people who use it in the literature. So let's see what is the Dobrushin criterion in this case. So in this case, to compare the is difficult. It's more involved, and as far as I know, no one used the Dobrushin criterion in this for this example of the countable of a polymer gas of a finite set of a countable set. In any case, to compare the Dobrushin criterion with the Kotevsky-Price condition, it's convenient to start from the Miracle-Soleil version of the Dobrushin condition. So I remind you, what did I do? What did I do? I remind you the Miracle-Soleil version of the Dobrushin condition, and I plug in this Miracle-Soleil version, I put mu tilde gamma equal rho gamma e to the a gamma, then the Dobrushin condition become this one, namely taking this here and this here, this one, dividing this factor by e to the a gamma became this one. So I can write down this condition as sum over gamma incompatible gamma 0 less or equal to a gamma 0, namely this term. So I can read the Dobrushin condition in this way. This factor, which is the same that appears in the condition of Kotevsky-Price, must be less or equal a plus this factor here, which is the inf over all polymers of these numbers. And in general, for gas of finite subset, this already go to 0. So the inf of this is already 1, so this is already 0, so this go to 0. So morally, the Dobrushin condition for the finite subset, for the subset, the gas of finite subset of a countable set, is like the Kotevsky-Price condition. Actually, it's a little bit better because for small polymer, this number is there. Okay. Well, let's see our condition. What our condition gives for this particular case. So we will choose again in our condition mu gamma equal to rho gamma e to the a gamma, and so our criterion become this must be this partition function. Mu is calculated at its values must be less or equal to e to the a gamma. So the partition, so this criterion write down like this. Now notice that the sum here is 0 whenever n is greater than gamma, because there is no way to put more than n polymer in such way they are all compatible and all incompatible with a given polymer with cardinality n. So when the sum above is non-zero, namely when the cardinality of gamma here is the opposite. When the cardinality of gamma, when the cardinality of gamma is well, where n is less or equal to the cardinality of gamma. Okay. We have a very raw bond. So the first polymer has intersection gamma and the sup. The second polymer has at least 1 point less, so gamma minus 1 and so on. So this guy can be written in this way with this binomial factor. So plugging this in the partition function, I get this, and I can rewrite like this. And so our criterion becomes this, which we can read like this. So it's very similar to the Kotevsky-Price criterion, but instead of A, so it's a criterion, let's say, uniform in gamma, which I can test for every gamma, but instead of A, I have e to the A minus 1, which is better. What is curious as...
Question, if the rows aren't necessarily positive, is that
Yes,
correct?
yes.
So if they are alternating in sign or something, this could actually take advantage of that somehow. Makes it less restrictive.
So the rows are
The row are positive.
So the rows are
Row
so the upper bound. Okay.
it's an upper bound, yes. The row are positive. So what is curious is strange that this very same condition was also given in the paper by Gruber and Kunz in 1971, but no one used this condition. The only difference is that instead of e to the A there is c, but the condition is exactly this. Strange things of cluster expansion. So let's prove in the second part of the talk. I will try to prove our criterion. So we start. This is the K point. We start with an upper bound of the Ursel factor appearing in the series we want to show the convergence. So let's introduce some notation. I will call T0n the set of all labeled trees with vertex set 0, 1 to n, and I think this tree is rooted in 0. In a rooted tree, vertices are always can be thought as partially ordered. So each vertex has a unique parent E, each vertex C has a unique parent, which we will denote sometimes by E prime, and SAE children denoted by E1, ESAE. The number SAE is also called the branching factor of the vertex E. Of course, the root has no parent. We also denote the tree distance of the vertex E from the root. D is also called the generation number. If E is a vertex of tau such that SA equals 0, then it is a leaf. It's also called an endpoint. So fix now an ennople gamma 1, gamma 0 in the Cartesian product of P n plus 1 times. We recall that G gamma 1, gamma 0, gamma n is the graph which appears in the sum of in the definition of the Ursel coefficient. Is the graph with vertex set 0, 1, n, and we just set given by this. Right, a set Ej, a pair Ej in 1 to n is in E gamma 0, gamma 1, gamma n, if and only if gamma E is incompatible with gamma j. So suppose also that this graph is connected, otherwise it's trivial, the bound is trivial because the Ursel coefficient is 0. And let us denote like Tg di gamma 0, gamma 1, gamma n, the subset of T0n, the rooted tree, given by this, ossia, the three which are in T0n, such that they are spanning tree of this graph. They are spanning subgraph of this graph G gamma 0, gamma 1, gamma n. So once we have this, let us define what is a Penrose tree. So take a map P that to each tree in this set I have just defined, and associate a graph P di tau, which is a subgraph of the graph G gamma 0, gamma 1. And this graph is formed by adding to T all edges which are in e to the gamma 0, gamma 1, gamma n, and minus e di tau. E di tau is the edge set of tau, such that either Ej are siblings, or namely children of the same parent, or the distance from E to the root is equal to the distance from J to the root, or the distance from J to the root is the E minus 1, and J is greater than E prime. E prime is the label of the parent of E. So notice that P1 is redundant, because if this is superfluous, because if this is satisfied, clearly also the siblings which are at the distance, which are the same distance to the root. But I write P1 explicit because for later convenience, because I will drop these two other a few slides ahead. So the Penrose tree which is a subset of G di gamma, the Penrose tree of G di gamma 0, gamma 1, gamma n is defined as the three which are spanning sub 3 of G di gamma 0, gamma 1, gamma n, such that PDT equal T. PDT equal T means what? So a Penrose trees of G di gamma 0, gamma 1, gamma n satisfy what? First, this condition, that if J are in E tau, then Ej is a subset, Ej is an edge of E di gamma 0, gamma 1, gamma n. This means that gamma E must be incompatible with gamma J. The second condition, if two vertices Ej are siblings, then Ej doesn't belong to E di gamma 0, gamma E, gamma n, because P tau equal tau. Then this means that gamma E must be compatible with gamma J. The second and the third condition as the translation of the condition of the map, namely, I don't even say this condition because I will ignore this condition later. So the property T0 is simply the fact that T is a spanning subgraph of G gamma 0, gamma 1, gamma n. And T1 is in fact superfluous, because if T2 is true, T1 is true. But again, we will explicitly write T1 for later convenience. So the Penrose identity is the following. The Husserl coefficient is equal to the modulus of the sum over this is the definition, and this is equal to the sum over all three graphs, spanning three graphs T di G di gamma 0, gamma 1, gamma n, such that P tau equal to, namely the sum over all, namely the cardinality of the set of Penrose trees of gamma 0, gamma 1, gamma n. So this is an identity. It's easy to prove this identity, let's say. I have the proof, but it's in the appendix. So if there will be time, I will prove this identity at the end. In any case, let us use this identity. First, let's do a remark. If I ignore altogether the condition here that P tau equal tau, namely that tau must be a Penrose trees, I get this bound. The Husserl coefficient is less or equal sum over all spanning three graph of G di gamma 0, gamma 1, gamma n, which can be written in this way, let's say. This is the so-called trigraph bond, rota bond, Penrose bond. Everyone can. There are. It has not a definite name, let's say, but it's the bond which has been used in the literature during this year. In particular, you have seen this bond also yesterday. Alan Sokal presented you this bond yesterday. But we will go beyond this bond using the Penrose identity. So let's define a family of trees which we call the weakly Penrose trees as follows. T is a weakly Penrose trees. We denote this set with P star of G di gamma 0, gamma 1, gamma n. Tau is a weakly Penrose trees if T0, the first condition of the Penrose trees, is satisfied, such if Ij must be an edge of E di gamma 0, gamma 1, gamma n, namely gamma E must be compatible with gamma j. And T1, if E and J are siblings in tau, then Ij doesn't belong to E di gamma 0, gamma 1, gamma n. Namely, gamma E, gamma j must be compatible. So I simply ignore the other two conditions of the Penrose trees. Well, with this definition, I have immediately that the set of Penrose trees contain this set, which is contained in this one. So this allows a bound beyond the rota bound of the Ursel coefficient is this phi di gamma 0 gamma 1 modulus of phi t di gamma 0 gamma 1 gamma n, which is equal to the sum over all Penrose trees in gamma 0 gamma 1 gamma n. This is less or equal the sum over all weakly Penrose trees, which I can denote like this, which I can explicitly denote like this. You know that for each vertex E, the children of a vertex E must incompatible, the children gamma j vary from 1 to SE, the branching factor of the vertex E, must be compatible with gamma E, and all the siblings must be compatible. So we have the upper bound, so I write down here explicitly the upper bound. The upper bound we get is this. This upper bound is beyond, it's a better upper bound than the three-graph bound. So presumably will be an improvement on the convergence radius of the cluster expansion. Well, so our objective was to check the convergence of this series. I rewrite this series englobing this in this way. Instead of starting from 1, I started from 0, and I use the convention that the term equal n equals 0 is 1. So plug in the bound 3. This is because the formula are too big otherwise, just for this. And plug in the bound, our improved bound on the Ursel factor in this formula. I get that this series is less or equal another series, and the other series has this shape. So it's the sum over n going to from n to infinity, 1 over n factorial, sum over tau belongs to tau 0 n of C tau rho. C tau rho is this factor here. I simply substitute the bound. Now the next step will be to reorganize this sum. This sum here, the sum goes over labeled 3 in the set 1, 2, 0, 1, 2, n. But this factor, C tau rho, actually does not depend on the labels, because here there is a sum over the label. Gamma 1, gamma n are dummy indices. Depend only on the branching factor associated to each vertex E. So with this observation we can reorganize the sum over label 3 in P star gamma 0 as follows. We need to define what is a plane rooted tree. At which label rooted 3 tau we associate a drawing in the plane. The drawing tau is obtained by putting parents to the left of their children, which are then ordered from top to bottom consistently with the order of their labels. This drawing is called the plane tree associated to tau. So for example, suppose that A is the label tree in the set 0, 1, 2, 3, 4 with vertex sets 0, 3, 1, 3, 2, 3, 1, 4. B is this one and C this one. So the plane rooted tree associated to this is this. You see that here there is 0, here there is 3, here there is 1, here there is 2, and here there is 4. And this guy is the plane rooted tree associated to this one, and this guy is the plane rooted tree associated to this one. This plane rooted tree and this plane rooted tree are treated as different, because the order here is different from the order here. Okay, so let's introduce some more notations. So I denote like T0, this strange T0n is the set of all plane rooted tree with n vertex and fixed root. we also denote by this symbol the partial alter among the vertices in a rooted tree. So if U and V are vertex of T, we say we say that U precede V and write U precede V if there is a path from the root to V which contains U. If VU is an edge of a rooted tree tau and U is a parent of V and V is side, then of course U precedes V. We also recall that for a given edge, SV will denote its branching factor and its children are denoted by V1, VSV. So let's go back to our series. Now the series which is actually majorized the series we want to show the conversion, which was this series. The factor C tau rho is this factor. Depend only on the plane rooted tree M tau equal tau associated T, namely can be written as follows, as the product over all vertices which follows the root, which are greater than the root of sum over gamma V1, gamma V0. Here there is the condition. In each vertices, the children has to be incompatible with the parent and the siblings must be compatible. So this sum can be written as the sum over, now I reorganize this sum as writing the sum over all plane rooted tree in the vertex with one root and any vertex, then the sum over labels tree which give the same plane rooted tree of this factor, but this factor depend only on this tau, so came out of the sum, then I'm left with this factor, and it is to see that this factor is n factorial divided the product over the branching factor in the vertice. Because n factorial is the way I can distribute the labels in the n vertices, but in each vertex I have to choose only one of the SV factorial order. So this is the number. So we obtain that our series, or the series majorized series, can be written in this way, or written in a better form, in this way. Sum over n equal to 0, sum over plane rooted tree with any vertex and the root of this factor, and here I put T0, the union of all rooted trees, so in a more compact way in this form. Sum all the plane rooted tree. This guy. Okay. So now, now let's keep in mind this formula and we change subject. We made a generalization of the Lagrange inversion formula. So let's take a function mu from the polymer space, a positive function mu, which to gamma associated positive band, and define for each gamma the numbers R gamma as R gamma is mu gamma divided phi gamma nu for all gamma. And phi gamma is some function which has the distractor 1 plus sum with n greater than 1, greater or equal than 1, gamma 1, gamma n in the Cartesian product of the polymer space. This function mu di gamma 1, gamma n. This function bn di gamma, gamma 1, gamma n is a function, is a positive function that can also be 0 sometimes. So let us denote T gamma mu, R gamma mu, phi gamma mu. So this equation can be rewritten as mu gamma 0 equal T gamma mu for all gamma 0 belonging to P. This equation can be visualized in this way. Here mu gamma 0 is a bullet equal to T gamma mu 0, which is a circle dot plus a circle dot minus a straight line minus a bullet plus a bullet and so on. So as the circle dot is R gamma 0 and this guy is R gamma 0, sum gamma 1, gamma n belongs to Pn, Pn gamma 0, gamma 1, gamma n more gamma. I just rewrite this, putting this here In this way, it's clear that this equation can be iterated. So I can replace the bullet at the end point of this plane rooted tree with one generation with again all the expansion. So I can rewrite the circle, the bullet as an expansion in terms of plane rooted tree with 2 generations, then with 3 generations, then with car generation. So with this representation, the k iteration of t, which is always give mu, involve all possible plane rooted tree up to the k generation. In each term of the expansion, the vertices of the k generation are occupied by bullet, and the other vertices by open circle. So in particular, the k iteration of mu can be written r gamma 0 sum to with L going to 0 from 0 to k minus 1 of this guy plus a rest. This guy here is the sum over all 3 with the L generation weighted by this factor. This factor has a similar expression, but the activity in the k generation are weighted by mu instead of that rho gamma 0. Since this is always true for every k, then we have that this sum is less or equal than mu d gamma for all k belonging to n. This immediately implies, because if I let k to infinity, this becomes the sum over all plane rooted trees. So I immediately have this proposition. Take a function mu, a positive function mu in the polymer set, and define for each gamma in P the number R gamma as this one. Let phi gamma be this function, then this series here converge, and rho gamma times this series is less or equal than mu. And this is the infinite iteration of the map we're seeing there. But now we are done, because this series, let us compare this series, this one, 4, 9, with this now. They are the same series, and here explicit there is the factor. So they are this series can be identified if one choose b gamma 0 as this factor, which is this factor here. Thus phi gamma 0, thus phi di gamma 0 gamma n is this factor, which is the partition function which we were speaking in the beginning. And so we get, using the proposition 3, we get immediately our criterion. If rho gamma is less or equal than R gamma, which is mu gamma divided phi gamma mu, which is in this case is xi p gamma 0 mu, then the series p star gamma rho is finite for each gamma 0 and is bounded by this. So in particular, the series which we want to bound is majorized by this series. So we have the criterion 1. To conclude, you see that this technique yields, with this technique you can also obtain the other 2 criteria. Just relax in three here, in this formula, here the sum over gamma v1, gamma v has 2 conditions. If this condition, instead of saying that gamma e must be compatible with gamma v must be compatible with gamma j, I said that it must be different, which is a weaker condition. So if I put here different, this sum will become greater than our sum, and this here the Koteski price condition, the Dobrushin condition. So in 3 doji, I replace the condition gamma vi, gamma v by the weaker equivalent gamma v different by gamma v. We obtain a new series which we call p gamma 0 Dobrushin. Again, p star is less or equal this. All the things follows. Now this coefficient is this, so the phi gamma Dobrushin is the Dobrushin factor. So the proposition in 3 in this case yields the Dobrushin condition, and the Koteski price condition the same. If this condition is cancelled, ignoring in the formula 3 312, then I have the Koteski price condition. Namely, the Bn now are this as just this factor. The function phi gamma 0 Koteski price is this, which is the exponential of sum over gamma 0. So the convergence is this. And in this way, it's very clear what you are losing with every one of these criteria. You want with our criteria, we are using this condition, that the siblings must be compatible. In the Bruching criterion, this condition became the siblings must be different, which is weaker. And in the Koteski price criterion, the condition became the siblings are what they like. And okay. So this is the end of the talk.
Any questions?
Can you systematically improve on this criterion by taking more and more of the Penrose conditions?
Yes, well, we didn't do that yet, let's say. But this is one of our objective in the future. Another direction is also try to improve this criterion by because here we are at level 3. Our interaction is our core, but we can also think in different interaction. And actually, there is a preprint by William Faris which which extend our criterion also for just positive interaction. So so it's possible to extend our criterion for positive interaction. There are various directions we are still working this, let's say. Yeah.
David?
For the dominoes,
Yeah.
does anybody know what, in a numerical sense, what the real radius is?
I don't know.
It would be nice to know how far off.
Yes. But
This criterion, you take into account the triangle diagram. So the ideal case, the case in which this criterion is optimal, is the complete diagram.
But
Give you an idea how far off you are in another graph.
I don't know how far we are from the real convergence radius. Yes.
So here's a kind of crazy question. You mentioned that what you were trying to do is to solve an equation by something analogous to Lagrange inversion.
Mm-hmm.
And so you have this iterative method which allows you to solve the equation. But there actually is a multivariable Lagrange inversion.
I'm let's say I'm completely. I don't know if there is.
There actually is. In fact, you know about this. Right? There is a multivariable Lagrange inversion formula.
But the problem is that the number of variables is infinite. So.
Well, so there's a research topic. Did your paper do it in the case when you're in?
Yeah, and it involves sums over trees.
Mm-hmm.
It involves sums over trees.
I thought it involved some determinant.
Did you call it the Lagrange inversion formula?
Well, the Lagrange good.
Okay. So.
Involves some terrible determinant, doesn't it? You haven't tried it, okay.
Okay.
Yes?
So you are, for your criteria, you are counting Penrose trees, but in fact this is an evaluation of the top polynomial, and you could evaluate it by another mean. I mean, here you are want to make an inequality in order to approximate this number of trees, but you could use different kind of activities and try to count them really.
Yes, yes. For example, one of the things that in which we apply this bond is exactly in order to improve the Sokal result on the zero of the partition function of the chromatic polynomials. Let's say it's possible to do this.
And for instance, this is also the number of root-connected acyclic orientation. So there are other way of writing these numbers.
Mm-hmm.
So I don't know, maybe for some example, some activities will be better suited on.
Yes.
Yeah, so I just want to raise an open problem. I mean, one reason that I was so scared of the cluster expansion for 25 years was all of this combinatorics of trees. And so I finally got seduced when I saw the de Bruijn proof, which proved valid for level 2 or level 3, but it's just this simple inductive proof with functions a plus bw. And so what you have here is at level 3.
Yes, it's a
iron
level
or
3.
gas.
Yes.
So it's natural to expect that there should be a proof of your criterion which improves de Bruijn by some de Bruijn-like inductive method. And I'm embarrassed to say that Roman and I tried hard and failed. So open problem, get rid of all the combinatorial trees.
Yes.
And prove your beautiful criterion by a simpler method.
I don't know. Let's say yes. Roberto, do you want to answer to this question?
Well, no, I have a partial answer and a hopeful answer. The partial answer is the Gruber-Kunz criterion can be proven inductively exactly in the same way as the.
Can you speak up, please?
The Gruber-Kunz criterion. So this the thing you obtain from our condition for the geometrical polymers, for the subsets polymers, this can be proven inductively, exactly in the same way as the Bruijn. This is something.
But you don't immediately see a way to extend that to the abstract.
No.
Yeah, and then to the abstract, there is a hope, because if you look into the proof, actually you end up with a sum over trees, and this sum you bound inductively. Okay? So there is an induction in the game, but at the level of this sum over trees. This suggests that if there has to be an induction at the level of partition functions, it's at the level of composition of partition functions, not of this deletion, addition identity, but composition. You have to take the partition function where the fugacities are themselves partition functions, and get an inequality of this type, and that you should prove inductive.
But
This is hope.
Can I make a remark on Ellen's remark? I think that you can do the Tedeschi-Price criterion with no combinatorics whatsoever. No trees, no nothing. And that's fairly easy. On level 1, even. But for the Fernandez-Procacci thing, I struggled to try to do it without combinatorics and trees, but I couldn't do it. I can do it on level 1 with some combinatorics of trees, but it's a little harder.
It's only on level 2 or 3 where I would expect that there's some simple induction, because then the partition function is a multi-affine polynomial in the fugacities. So open question for anybody like me who's afraid of combinatorics.
Right, combinatorics. You have 5 minutes to do that proof of the.
yeah, sure. So let's prove the Penrose identity. So to prove the Penrose identity, I define a map Q that associates to a graph G, which is a subgraph of the, which is a Spanish subgraph, which is a Spanish subgraph of G gamma 0, gamma 1, gamma n, a unit tree, which is a subtree of G gamma 0, gamma 1, gamma n. So again, I have a graph G, I denote dGe, the distance of the delta x from the root. So we construct the tree QG by first deleting all edge ij which are in a G such that they are at the same distance from the root. After this operation, what I get a connected graph G prime such as the same as always dg prime E equal dge. Here I'm replying the demonstration of Pfister which appear in Pfister, because we learned the Penrose identity by through an article of Pfister. After this operation, moreover, each edge ig of this new graph G prime is such that the distance dg prime e minus dg is 1, because all the other is, I already cancel out. Now, for any e different to the root, now I delete all edge ij in G prime such that dg prime j equal dg prime e minus 1, except the one with j minimal. So what I get is still a graph, a spanning connected subgraph of G gamma 0 gamma 1, which by construction has no more cycle. So it's a tree.
May I just interpolate here? So this Q of G is the breadth first tree that you generate by breadth first search starting at the root.
Yes, I suppose. Yes.
I mean, that was just a translation.
Okay.
Just a translation. I am, but the little part of combinatorics I understand. I was trying to do a little translation.
Well, I felt like perhaps there's also a condition on the comparing the numbers of the vertices to get a unique depth first, a unique breadth first search.
Yes, a breadth first search where you always take the lowest
Yeah,
numbered child, lowest numbered child.
So I constructed this map. Conversely, if tau is a tree of which is a spanning subgraph of G gamma 0 gamma 1 is given, and if G is such that QG is equal time, then by the definition, the map MP that we have seen before is such that tau is contained. It's a sub-spanning subgraph of G, which is a spanning subgraph of P d tau. So P tau is a Boolean interval. So P tau is the maximal graph respect to the spatial order, respect to the relation among those graphs, such that QG equal tau. With this definition, then, so what we can do? We have this sum. We reorganize the sum over 3 belonging to this G. This factor here, I pull out the factor of belonging to the 3, and then I have to do the sum over all graph G gamma 0 gamma 1 such that QG equal tau, and what I left is this factor, AG minus A tau minus 1. You see that this time this give again this, and this time this again gives again this. So this factor is minus 1 to the n, this for each graph. Then this factor here is plus 1 minus 1 to this factor, because here are some of all sub-edge of the maximal graph such that QG equal tau, which is PT. So this factor is equal to this, and you see that this factor is always 0 unless P tau equal T. And this is the Penrose formula. You see that with this demonstration is also proved that the coefficient have the alternate sign property. This alternate sign property was something known since a long time ago. Okay. Well before a long time ago. The Penrose formula is pretty old. Okay. So this is the proof.
All right, let's thank the speaker.